GeneGAN, learning object transfiguration and object subspace from unpaired data, and it's going to be presented by Shuchang Zhou.
Good morning, everyone. I'm Peng. The authors of this work are Shuchang, Zhou, Taihong, Xiao, Dieqiao, Feng, Qinyao, and Weiran from Megvii. The authors didn't come here and they asked me to present their work, so I'm sorry that I need to read their notes. I will still use we to refer Z. The title of this work is GeneGAN, which is a method to learn object transfiguration and attribute subspace from unpaired data. So what is object transfiguration? It is a type of conditional image generation. In other words, we not only generate image, but also require the generated image to satisfy certain conditions. For example, we want the generated image to contain a specific person and a given background. Since conditional image generation allows us to have more control over the generated image, it can be used for editing an existing image. Moreover, it can be seen as a powerful method of image augmentation, which is very useful for synthesizing data for the data-hungry deep learning models. The traditional computer graphics approach to object transfiguration is made up of these steps: modeling, transformation, and rendering. However, photorealistic modeling and rendering are often hard and engineering intensive. In contrast, the feature space transformation method exploits the linearity of the feature space extracted by deep learning models to transfigure the object. For example, in deep feature interpolation, a method proposed in 2016, magic transformations can be done in the projected feature space, like changing the age, making a smile. Here are a few examples of adding layer to the photo. In contrast, the addition of layer is done by adding a transformation vector V to the projected feature phi. When the transformed feature is projected back to the image space, the result will be the original photo with layer added. Neither explicit modeling and rendering of faces nor extraction of landmarks are involved in the process, and the results are photorealistic. However, one of the key difficulties is getting the transformation vector. DFI uses the difference between centers of clusters in feature space as transformation vectors, because the diversity of the generated image is limited by the number of clusters. In other words, it can transform a face to have a beard, but not the beard. This means that generated image will have more or less the same beard. In addition, the feature space is not fine-tuned with respect to the transformation task, because it is tricky to find the correct transformation vector. On the other hand, there was a line of research that tries to increase diversity of generated image by using exemplar pairs. For example, on the left are a script x1 drawing the ball and another script x1 prime not drawing. As the two images contain the same script, their difference should stand for the action of drawing the ball. When the transformation vector is added to another script x2 prime, which is not drawing the ball, we will create a null image of x2, showing a script drawing the ball. This visual analog method requires full annotation of the four scripts. In the later work of disassembling factor of variation, the annotation requirement has been realized by using an adversarial training and cyclic losses. Nevertheless, paired training data are still required. We know that such paired training data are hard to collect, especially in the controlled environment. For example, if we want to learn a transformation vector standing for smell, we would need to have two photos of the same person, one smelling and one not, and with the same hair, dressing, and clothes for this method to work. So we have seen two approaches to conditional image generation. One is based on unpaired training data but lacks in diversity. The other uses exemplar pairs which is hard to collect. So we can combine these two approaches to have the best of two worlds. This is what we aim to do with GeneGAN, a method to learn transformation vector from unpaired exemplars. For training data of GeneGAN, we require there be two sets of images. One is the positive set which contains images that have all kinds of objects, and the other is the negative set that does not contain the objects. There is no more requirement than the 0-1 labeling of the image. The examples of such labeling are listed in the table. The positive side can be image wearing glasses, and the negative side contains images that simply do not have glasses. For other kinds of objects like pairing and lighting, the negative side can still be defined by not having something semantic. Hence, frontal lighting and not smelling can make up the negative side. Based on the positive side and negative side, GeneGAN can learn to separate objects from background. The building blocks of GeneGAN is the same as in disentangling factors of variation, an encoder that projects an input image to two feature codes, one for background and one for object. Note that the object here can be abstract, like smelling. The decoder in its reverse of encoder, that it combines two features code to generate an image. We use epsilon to represent a non-object. The output of encoder is combined to the decoder, where we would expect the exact reconstruction be produced. Before diving into the training of GeneGAN, we will play with the decoder for a while and get familiar with them. For example, we can remove an object by supplying the non-object instead of the original object to the decoder. The background information will be preserved while the object is removed. In this example, we are able to make a no instance non-smelling phase use GeneGAN. Moreover, we can swap the object from two images with the encoder and decoder by swapping the object codes of two images. Here gives an example of swapping the lighting condition of two faces. We know that the lighting are hard to specify as the shadows are determined by the light source and 3D shapes of faces. Anyway, as long as the decoder can separate the object and background, we can swap the object even though we don't know how to specify the object. We know that identity information is preserved through the transformation process. Next, we show how to train GeneGAN. We pick two images, one from the positive side and one from the negative side. We require the two children to have different labels than their parents. This is done by using an adversarial trainer to ensure that the child BU is indistinguishable from the positive side, which implies two things. First BU is smelling, second BU should be a photorealistic face. Further, as the combination of decoder swaps the object of two images, we can apply twice and get grandchildren. We are theoretically exact reproduction of the first row. We know that there is an underdetermined problem with CycleGAN for the positive-negative training data. For example, in the CycleGAN diagram, a smelling face is generated from a non-smelling face, and this step generates something from nothing. This style of smelling is often stereotypical and lacks diversity. Another example is eyeglasses, for which CycleGAN will often produce black-green glasses. In contrast, in GeneGAN, we know that the object carries the smelling information, flows down and up, and is preserved along the whole process. To further improve the stability of training, we propose a one-generation diagram that shortens the cycle. We know that the children and the grandchildren of two parents can all be produced in one generation. Following the diagram shown on the right, now there need be only one round of encoding before the four combinations are generated. Here is the final training diagram of GeneGAN. There are four children, which are a recombination of background and the object code of parent. There are two children, AU and B epsilon, that have the same feature as the paired perspective and should be exact reconstructions. The constraint is reflected by the presence of two reconstruction losses in the diagram. There are also two novel recombination A epsilon and B, which are like crossbreed in the biological reproduction. To ensure that this crossbreed have the desired properties, two adversarial discriminator are used to ensure the A epsilon and B should belong to the A epsilon should belong to the negative side and B belong to the positive side. Here explains some details of the losses in addition to the discriminator losses that ensure the crossbreed belong to the correct category. We also have a knowing loss that ensures the object code of image of negative side to be 0. This will present backward information from snaking into the object code. On the other hand, the reconstruction loss ensures that no information is lost in recombinations. Next, we see GeneGAN in action. In this example, we check the ability of GeneGAN to transplant eyeglasses. It can be seen that the transplanted eyeglasses stay as eyeglasses and the sunglasses stay as sunglasses. This showcases the diversity of generated examples. GeneGAN can also be used to swap the attributes that are hard to describe. In this example, the smelling is swapped between the two parents. It can be observed that the hairstyle follow closely the source image on the top row. In fact, the direction of hair are in good agreement with the source image. This figure gives interpolation of object features to attribute subspace. Note that background which are human identities are approximately the same, while the hairstyles are interpolated between the four corner exemplars. This shows that the object codes cannot only be swapped, but can be interpolated to construct novel instances that are still meaningful. The interpolation operation further increases the diversity of generated examples. Here we summarize our work. GeneGAN is a method to learn disentangle the vector in feature space into two sets, one for object and one for background. The training data consists of positive and negative sets, which helps to characterize the object. The training GeneGAN model can be applied to several tasks, including removal of objects, swapping of objects, and the interpolation of objects. Here are some references, and the code are available at GitHub. Thank you for listening. I may not be able to answer the questions, so if you have some questions, please contact the authors.